In the previous video, we talked about the notion of a residue, and in this video, we talk about how to compute residues, and we're going to do that especially for the case of poles. So just to recap, if z0 is a pole for a function f of z, then two things are true. First, f of z can be written as h of z over z minus z0 to the power of m, where h is an analytic function on the disk modulus z minus z0 is less than r. And the second thing is that the pole has an order, and the order is m, and usually you can pull the order off just straight off this exponent here. So this is a pole of order m. So again, moving on now, we're going to say that since h is analytic on z minus z0 modulus is less than r on that disk, that means it has a power series expansion on that disk. That's something we learned about before. So we can write h of z as a power series. We can write it as sum from k equals 0 to infinity of c sub k z minus z0 to the power of k. And that's true inside of the disk right here. So that means f of z being h of z divided by z minus z0 to the power of m. That means we can just take this whole power series here and divide it by z minus z0 to the power of m. Which means that what's the first term? Well, the first term of h of z was c sub 0, right? Because this term just equaled 1. So c sub 0 divided by z minus z to the power of m is right there. And then we go on, what's the m minus first term? So it's going to be c sub m minus 1, z minus z0 to the m minus 1, divided by z minus z0 to the power of m. So we're just going to have a single z minus z0 here. And this term is going to turn out to be very important in just a second. And then we just have the rest of the terms. This term is just c sub m. It's just a constant, because really, it's going to be c sub m times z minus z0 to the power of m divided by z minus z0 to the power of m. So just going to be, it's going to cancel out, and we're just going to have c sub m. And then we're going to have the rest of the terms here. So we see that there's like two categories of terms. These terms all have negative exponents. Really, it's going to be exponents in the denominator, but this is really z minus z0 to the power of negative m. This is z minus z0 to the power of negative 1. And these have positive exponents. And this is just a lone term with no exponent. Exponent 0. Okay, so now we want to compute residues. And if we recall from the previous video, residue of f at z0 is given by 1 over 2 pi I integral of f of w dw over any circle. We said that's independent of the circle as long as the circle is less than, the circle must be radius less than r. Okay, so we want to now consider how to compute this, and this computation seems very difficult at first, because what we did here is we took f of w and we just plugged in this whole thing right here and just stuck it in for f of w, and now we have to compute this. This seems very difficult, but it seems it's going to be very elegant after we figure this little point out. So we're going to consider this integral. We're going to consider 1 over 2 pi I integral of z minus z0 to the power of j dz, and it's going to be over some circle with radius s less than r. Now we're going to consider it for two different cases. Consider it when j is equal to negative 1 and j is not equal to negative 1. And j is always an integer, okay? That's the j right here. So now we're going to consider for j is not equal to negative 1. So the first step is going to be to parametrize. So we learned about how to parametrize the circle. So the contour, or the curve that we are doing this around, is going to be the circle z minus z0 modulus equals s. And we learned how to parametrize the circle. It's going to be center plus radius times e to the I theta, where theta goes from 0 to 2 pi. So we're going to transform the integral into a integral from 0 to 2 pi. This 1 over 2 pi I stays on the outside. And then now we have to put f of w. So it's going to be, if we recall back here, we have to put z minus z0 right here. And what's z minus z0? Z minus z0 is just going to be this term right here. It's going to be s e to the I theta. So we're going to put that right there to the power of j, and then furthermore we have to put z prime, or dz d theta, and that's going to be given by s times I e to the I theta and then d theta. Okay, so that's just taken straight from this, because z equals that. We take the derivative with respect to theta and we get that right here. And one nice thing is that this I out here cancels with this I over here, and then so we don't have to worry about that I anymore. And then what we're left with is s to the power of j, which is here, a single s, which is here, e to the I theta to the power of j times e to the I theta. So I put e to the I theta j plus 1, just factoring out the exponents and putting a j plus 1 right here. And now what does that equal? So I took this s and s to the power of j outside the integral because they don't have anything to do with theta, and I left this term inside. And then we're just going to go ahead and integrate, because this is just a regular integral. So we're going to have 1 over 2 pi on the outside, s to the power of j times s. And then this exponent we bring down, so it's going to be 1 over I times j plus 1. And then we're going to have e to the I theta, j plus 1 minus e to the power of 0. This 0 we obtain by putting in the lower limit 0, and then we sub in theta, we put 2 pi over here. And now this term right here is going to be equal to 0, because e to the power of 0 is equal to 1, and this is also equal to 1. And to see why it's equal to 1, it's because this is a 2 pi I. So e to the 2 pi I we know is equal to 1, and this is a j plus 1. So all this is doing is just putting a different multiple of 2 pi I. But e to any multiple of 2 pi I is equal to 1. So since this is equal to 1 and this is equal to 1, 1 minus 1 is 0. That means this whole integral, we don't even have to worry about all this complicated mess out here, is equal to 0. So we found that in the case that j, the integer j is not equal to negative 1, the integral is 0. And that's actually something really, really important, because this seems very intimidating at first, but we see that wherever the exponent is not equal to negative 1, for example here m, pretend this m is not negative 1, that means when we split up this integral into separate integrals with the plus signs, this is going to go to 0, all these over here are going to go to 0, all these over here are going to go to 0. So we still have to consider the case of this specific term right here, where z minus z naught to the power of negative 1. So let's consider that. J is equal to negative 1. So we're going to pick up right where we left off. So we're going to pick up from this step right here, where we have 1 over 2 pi s to the power of j s. And in this case, j is negative 1, so we have s to the negative 1 s. And then we have the integral from 0 to 2 pi e to the I theta j plus 1 and d theta. So now we have e to the I theta. What is j plus 1? Negative 1 plus 1 is 0. So we're going to have e to the I theta to the power of 0 d theta. And e to the I theta to the power of 0 is going to be e to the 0, which is going to be 1. So we're just going to have 1 over 2 pi. And s to the negative 1 times s is just 1. So this actually just cancels out, which is nice. No more s. And we just have integral from 0 to 2 pi d theta. And that's just going to give us 2 pi, which means 1 over 2 pi times 2 pi is equal to 1, which is also really nice, because that tells us that this integral right here is just equal to 1, and all we're left with is just the coefficient, c sub m minus 1. Okay, so that tells us that after we do this super complicated integral that looks super complicated to us at first, all that we're left with is just c sub m minus 1. That's all that's left, which tells us that what we were looking for, since we were looking for residue of f at z naught, that's just equal to c sub m minus 1. And of course, that's true from all these calculations over here. Okay, and now what is that also equal to? So I've written that it's also equal to this, and let's just confirm that it's also equal to this. So this is read as the m minus 1th derivative of h at z naught over m minus 1 factorial. So let's just see if this is true. So how do we find the m minus first derivative of h at z naught? Let's go find where h is defined. So h is defined right here. So the m minus first derivative, what's the first derivative of h? Well, it's going to be, if h we write out as c naught plus c sub 1 z minus z naught plus c sub 2 z minus z naught squared, and so on. The first derivative takes out the c naught, and then we have just c1. The second derivative will what? Take out the c1, and we're going to have 2c2. So what does that say for the m minus first derivative? So since the second derivative is going to be, at z naught is going to be 2c2, then the m minus first derivative is going to be m minus 1 factorial, because this 2 is actually just a 2 factorial. So if we took the next derivative, it would be 3 factorial here. So it would be m minus 1 factorial, c sub m minus 1. Okay, and if we want just m minus 1, we have to divide this by m minus 1 factorial. So it's going to be the m minus first derivative at z naught of h, and we have to divide that by m minus 1 factorial, which is exactly what we see right here. So it's going to be m minus first derivative of h evaluated at z naught divided by m minus 1 factorial. And this will be important for us in the next video. So the main point here is that the residue of f at z naught when we have a pole is the coefficient of z minus z naught to the power of negative 1. And this is a very, very, very powerful statement, because this means that if you can write your f as a power series, and you can do that when you have a pole. If you have a pole, you can just take this term right here, divided by z minus the power of m, and then you have yourself a nice power series, which has both negative and positive exponent terms. You just have to identify the term that has the coefficient of z minus z naught to the power of negative 1, which in this case I have underlined in purple before. And once you find that coefficient, that is the residue of f at z naught. So that's a very powerful way to do it. And let's just do 2 examples to kind of solidify our knowledge now. So the first example says, find the residue of f of z equals e to the z over z minus 1 to the power of 3 at z naught equals 1. So we see that we want z naught equals 1. We want this centered at 1. This is a little bit of a problem, because we have this bottom denominator is centered at 1, but we don't have this top part centered at 1. But we can easily do a little bit of trickery to make it centered at 1. So e to the z is actually equal to e to the z minus 1 times e, or e to the 1, because if you add the exponents, you get back e to the power of z. So now this e, I'll keep on the outside, and this inside part, I'll just expand in the e to the z. So in a previous video, we talked about the power series for e to the z, and we can write it for e to the z plus 1 just by substituting z for z plus 1. Okay, so we're going to have 1 plus z minus 1 plus z minus 1 squared over 2 factorial plus z minus 1 cubed over 3 factorial, a factorial plus z minus 1 to the power 4th over 4 factorial, and so on, just like that. And then when we multiply, now when we want the whole function, e to the power of z over z minus 1 to the power of 3, all we have to do is just take this e, we put it back inside here, and we divide all of these terms by z minus 1 cubed. So let's do the first two terms to see what happened. So the first term was 1. What do we do first? We have to multiply by e, which is why there's an e here, and we divide all that by z minus 1 cubed, which is why the first term of this is e over z minus 1 cubed. Now what's the second term? The second term was z minus 1. So again, multiply by e and divide that by z minus 1 to the power of 3. So z minus 1 over z minus 1 to the power of 3 is 1 over z minus 1 squared, which is why we have e over z minus 1 squared. Now here's the term we're interested in. This is the term which contains z minus 1 to the power of negative 1, right? Because we have 1 over z minus 1, which is the same thing as z minus 1 to the power of negative 1. So if we want the residue, we don't even have to evaluate these terms. I just put them for the sake of completeness and just to see the pattern. But really all we have to do is take this red term right here and pull off the coefficient. And what's the coefficient? It's e over 2. So that means the residue of f at 1 is just going to be e over 2. And that's the easiest way to do it. We just have to, the hardest part was probably to split this up as e to the power of z into e to the power of z minus 1 times e. Just understanding that. But as you do more examples, you'll see that there's different tricks involved. So the next thing we'll do is a theorem/example. And what we have to do is we have that f and g are analytic on this disk. Modulo z minus z naught is less than r naught. And furthermore, g of z naught is equal to 0, but g prime of z naught is not equal to 0. So next thing, we want to find the residue of f over g. So this is something new. We're finding the residue of a quotient at z naught. Okay, so what we're going to do is let this new function h equal f over g, which is a good first step because that's the function we want. Now we're going to have g of z is equal to z minus z naught times p of z. And why is this true right here? Well, it comes down to a few facts we know about g of z. We know g of z naught is equal to 0. Does this satisfy that? If we plug in z naught here, then we're going to get z naught minus z naught, so this is 0, so this whole thing's 0. That's true. Now let's take g prime of z naught. Let's take the derivative of this. Then we're going to have p prime of z times z minus z naught plus the derivative of this, which is just 1, plus p of z naught. And this is just using the product rule. So we see that if we plug z naught into here, this cancels out, but we plug z naught into here, we get p of z naught. And we have defined that p of z naught is not equal to 0. So the reason that we can write g of z as p of z times z minus z naught, where p of z is just some function, is that since g of z naught is equal to 0, we can kind of factor it out. So if you remember back from algebra, when you have g of something equals 0 or f of something equals 0, you can just take out a factor of z minus z naught from there, and then you're left with a new function right here. And this is not the p of z naught is not going to be equal to 0, because if it was, then we would have g prime of z naught is equal to 0, which it's not. So we have p of z naught is not equal to 0. And further, we know that p is analytic on modulo z minus z naught is less than r naught. Simply because the only reason it wouldn't be is if we had some problem with its denominator. So let's just rewrite p of z using this formula right here. So we can rewrite it as p of z equals g of z over z minus z naught. So we know that g of z is analytic on this disk right here. So we know that p is at least analytic on this whole disk except at the center at z naught. But what happens to p at the center? When we have p of z naught, we have g of z naught over z naught minus z naught. And since it's 0 over 0, it's undefined. But we can look at a simple calculation to see if p of z naught is indeed undefined there, or if we can give it a definition. So p of z naught is equal to what? Its limit as z approaches z naught of p of z, right? Because that's just how we define it. Now, p of z is the same thing as g of z over z minus z naught, okay? So then we can rewrite this as g of z minus g of z naught over z minus z naught, because g of z naught is just 0, so it doesn't change the numerator. Now this is just a definition of the derivative, so this equals g prime of z naught. So that means that p of z naught equals g prime of z naught. And what do we know about g prime of z naught? It's not equal to 0. So we know that p of z naught is defined because it's defined as g prime of z naught, which is not 0. So p of z naught has a definition, and furthermore, we already knew that p of z naught is not equal to 0. So now let's find what we're looking for. We'll find the residue of f over g at z naught. So we have h of z equals f of z over g of z, and we can rewrite this as f of z over p of z, z minus z naught, because that's what we can write. That's what we said we can write g of z as. So now let's go back to this definition of residue, where we had residue of f at z naught is equal to h, the m minus first derivative of h at z naught over m minus 1 factorial. So in this case, we need to kind of keep our letters straight and what's going on. So in this case, f, the function we want to find it for is actually h, okay, because that's f over g. And h is defined as what? H is the numerator of this f as f of z. So in this case, the h of z, what's the numerator here? The numerator is going to be this whole part right here. It's going to be f over p, and the denominator is going to be the part that's z minus z naught to the power of something. In this case, it's going to be the power of -1. So using this formula right here, we want the m minus first derivative, and in this case, what is m? Since this is to the power of -1, m is just 1, so we want the 0th derivative, or the actual function. So we want the value of the function at z naught over m minus 1 factorial. And what's m minus 1 factorial? It's going to be 1. So this doesn't matter for that. So we just want f over p at z naught, because that's our numerator. So what is f over p at z naught? Well, it's going to be f at z naught over p at z naught. So it's going to be f at z naught over p at z naught. And we define p at z naught as g prime of z naught. So that means that the residue is f of z naught over g prime of z naught. And this is kind of cramped down here, so let's make it a statement just to clarify what we're saying here. So we found that the residue of two functions divided, so f over g at z naught, provided that we have certain restrictions on g, where g of z naught is equal to 0, but g prime of z naught is not equal to 0. The residue is equal to f of z naught over g prime of z naught, which is pretty amazing because it's just simply given by the numerator evaluated at z naught divided by the derivative of the denominator evaluated at z naught. So if we know both of these, we know the residue, and we don't actually have to write out any series at all. So that's a pretty cool thing about residues. So this is just a little bit on computing residues. In the next video, we'll go over Laurent series and a little bit more on residues there.